Thank you very much, and thank you so much for inviting me to come talk to you this evening. So I thought we'd start off with a little trip down memory lane, for me at least, taking me back about 8 years or so. I'm sorting out my Zoom window, there we go. 8 years to a big talk that I was giving. And I was super excited because I was about to present some brand new results I've been working on for about 5 years by that point. But there'd been a bit of a childcare crisis, and so my son was very grumpily sitting in the front row. And I was just about to unveil this map of dark matter that you can see here behind on the screen. This is the largest ever map of dark matter that was made at that time. I was just about to unveil it when my son decided to jump up and shout out to this whole audience of people, "My mum doesn't know what she's talking about." Now my son's on the other side of this wall, actually, in the kitchen over there. And I said to him, "Right, everyone," and he said, "Oh, Mum, you're not going to tell that really embarrassing story, are you, about when I was 4 years old?" And I'm like, yes, I am going to tell that embarrassing story, because I think it's very useful, because I didn't know what I'm talking about. Indeed, no scientist knows what they're talking about when it comes to the dark side of the universe. So we know that it's there because of its effect on the things that we can see, like these glorious Hubble Space Telescope galaxies that you can see here. But if our models are right about the universe, this matter that you can see here, this luminous stuff, makes up less than 5% of the universe, and the rest is dark. Now there are two entities on the dark side. The first is called dark matter. I showed you a map of it. We'll talk about how I made that in a bit. It's invisible. We can't see it, but it's the strong gravitational force in our universe. And it's the gravity that pulls and keeps binding all the structures in our universe together. The second entity is called dark energy, even though it is neither dark nor energy. But if you call something dark energy, it's a good way of getting funding out of the Department of Energy in the United States. So that's why it's called dark energy. But suffice to say, we know very little about it, apart from the fact that it appears to be driving the expansion of our universe to accelerate, to get faster and faster. And these two dark entities are going to be the subject of our talk this evening. But what we're going to do is we're just going to make sure that my cat wants to get out of the door. I told it in that if I let the cat in, it would just want to get back out again. And now, pussycat, right, go, shoot. Right, now we get to do a timer to see how long it is till the cat wants back in again. Right. All right, let's make sure that we are all on the same page in terms of scale, because the universe is a very big place. So let's start off with the Earth. Of course, we know it's just one planet going around our sun, which is our local main sequence star. And our sun is just one star in over 70 million stars in our Milky Way Galaxy. All right, let's stop at the Milky Way Galaxy, because that's our first and probably most important evidence for dark matter. Because if you go and look at any galaxy that's out there and you measure the rotation of the stars within that galaxy, what you'll find is that the stars are moving too fast for the gravitational pull of the matter in the galaxy that you can see. So you know roughly how much a star weighs, and you can work out roughly how many stars there are in each galaxy given by how bright it is, and that tells you sort of the total amount of matter in that galaxy that is luminous. And then it's just a simple case of centripetal force versus gravitational force, and that tells you that these things are moving too fast. And the conclusion of that work, which was done by Vera Rubin back in the late 70s, early 80s, is that there is a massive halo of dark matter that surrounds all galaxies. Now, at this point, I like to gauge the opinion of the audience about what you think dark matter is. Now, normally we'd be sat in a lovely room together, and I've worked out a very, very scientific way to conduct polls now with groups of people. But I'm genuinely not sure if this is going to work on Zoom or not. And let me see if you are going to humour me this evening. You're going to need to unmute for this one. If you think that dark matter is utter nonsense, and what I just told you about stars spinning around, spinning too fast, is just my sums are wrong. I've got my forces and my gravity wrong. What I want you to do is to sing a high note for me like this. You're all like sat there, I know, in your kitchen's going, no, she's mad. All right, but if you think that dark matter is a new type of particle that hardly interacts with the stuff that we're made of, that we're going to find very soon, I want you to sing a low note, like that. Okay, so a high note if you think it's utter nonsense, and a low note if you think it hardly interacts with the stuff we're made of. And let's see if this actually works on Zoom. All right, everyone unmute yourself, and I'm going to give you a countdown. You have to humour me, otherwise I'm going to stop the seminar. Okay, right, 3, 2, 1. You are all brilliant. Thank you very much for humouring me. That worked better than I expected. Well, good. You're all believers. You're all believers in the theory that dark matter is a particle that hardly interacts with the stuff we're made of. And because you're physicists, I can take it a little bit more technical. Our definition of dark matter is that it's a weakly interacting matter particle. That means it doesn't interact through the electromagnetic force. If it did, then it would absorb or emit light. That we think it could act through the weak nuclear force. That's why it's a weakly interacting matter particle, but that hasn't been detected yet. And it certainly interacts through the gravitational force field. Now, often when I give this talk, I have a large contingent in the audience who sing hi, and they think it's utter nonsense. And I love these people and I salute them because, you know, we haven't found this particle. Your best theoretical evidence for it means that CERN should have already found this dark matter particle if it was weakly interacting, and it haven't. So I think it's important that we are skeptical, that we don't just take on board the basic theories that we're told. But I'm going to give you lots of evidence now to support this hypothesis of this dark matter particle. So let's continue going up in scale. So the Milky Way Galaxy is just one galaxy in many in our local group. Andromeda is a galaxy you can actually see with your eye. It just looks like a fuzzy star if you know where you're looking. And actually most galaxies live in a cluster of galaxies with hundreds of galaxies in there, all bound within this massive halo of dark matter. And if you zoom out onto the largest scales, and these are the scales that I work at, what you see is that there's this giant web of structure out there. The galaxies live in this giant web. And it's that gives us our next piece of evidence for dark matter. So I'm not sure if this is going to display well over Zoom. This might look quite jerky for you, but you can always find it on YouTube as well. This is just a fly through of the Sloan Digital Sky Survey. So this is a large survey that maps out the three-dimensional positions of galaxies. And what I want you to take away from this is that the galaxies aren't randomly distributed across the sky. They form this web-like structure. Now, if we simulate a universe that has dark matter in it, that is this weakly interacting cold dark matter, then this is what it would look like. And again, I'm hoping this is transmitting over Zoom okay. So what you can see here is when the color scale is sort of whitey yellow, that's when there's lots of dark matter. And as it goes dark, that's less dark matter. And if you just simulate the universe with a dark matter particle that interacts through gravity, then what you find is it forms these web-like structures. And our hypothesis is that the galaxies that we can see that have this web-like structure are just mapping out where the dark matter is. And it's the dark matter that dictates where and when the galaxies form in our universe. Okay, so this is just a static picture now of that cosmic web. So when I started my PhD, too many years ago now, far too many years ago, I thought, well, this is a lovely, lovely theory, but I want to actually be able to go and map out this dark matter. I know it's invisible, but I want to see it. I want to use a technique, develop a technique to map out dark matter. And so that's exactly what I did. And the technique that I use is called gravitational lensing. Now I'm going to show you, I'm hoping this movie will play over Zoom okay, but I'm going to show you a little movie now to explain how gravitational lensing works. This is my friend Phil Marshall, who's at SLAC, and this is an experiment that you can do at any romantic evening event with wine glasses and candles.
Okay, if I just look right through the base down here, I can see 2 images. Oh, there's 4.
Okay, so what's happening here, hopefully you can see that, is you've got a candle, and light from that candle is traveling towards Phil's eyes, but the curvature in the base of the wine glass, the different thickness of the glass, is bending the light in different ways. And so when he looks at the candle through the base of the wine glass, he doesn't see a single candle, he sees multiple images. Okay, so the base of the wine glass is lensing the light of the lensing the light of the candle, that's changing or distorting the image that he observes.
2 again.
Now, exactly the same phenomenon happens in space, except we don't have wine glasses and candles now. Our candle is a distant galaxy, and our wine glass is a massive clump of matter. So I've got another video here now. So I've got light traveling towards me across the universe, and that light is getting bent and distorted by the gravity of this big clump of yellow matter in the middle. Right, so Einstein told us that mass bends space and time, and so light doesn't travel in straight lines, it gets bent and distorted. And so let's have a static version of this now. So the idea is I go and look at images of very, very distant galaxies, millions and millions and millions of them. Their light, as it travels through the universe, doesn't travel in straight lines. It gets affected by the gravitational pull of all of the clumps of dark matter around it that are illustrated here in these kind of fuzzy clumps that are curving space and time. And so when I look at these distant galaxies, I find that they tend to line up with each other. And the amount that they line up with each other tells me how much dark matter is there and where it is. And so I can use this to map out all of the dark matter in the universe. So this is the kit that I use. We love big telescopes. This is Paranal in Chile. It is the most amazing observing site in the world. It has some of the best telescopes. This is the European Southern Observatory. I use 2 of these telescopes. The VST is here, which is the little telescope on the side. I'll just pause for a bit. Zoom's saying my internet connection's unstable. Eden, can you still hear me okay? You can give me a thumbs up or something to let me. Perfect. Okay, good. So the VST telescope is here, and with that we take images in the optical wavebands. And the other telescope down here is the VISTA telescope. This is a near-infrared telescope, and with that we take images in the near-infrared, and we combine all of that together to give us the deepest large-scale map of galaxies. Here are the different zoom. This is a look at what the telescope looks like on the inside. If you are into instrumentation, the camera that you can see here is pretty similar actually to the technology that's in your smartphone, just a lot bigger. Right, and you can't do science without lots of other scientists. This is my fabulous team. This project is called the Kilodegree Survey. They're a totally awesome team. a lot of us are based in the Netherlands, and so the last time we were there, I was like, we have to go and see every single tulip field in cyclable distance, and they humoured me. They're a fantastic team. So what we do is we take these images of these galaxies. This is just a little snapshot that we've taken, and hopefully what you can see is there are some big yellow galaxies and some little tiny blue galaxies, and there are some little red ones in there as well. The blue galaxies are in the background. They're really far away. Their light has probably travelled for about 7 billion light years through the universe. The big yellow galaxies are in the foreground. They're only about a couple of billion light years away. So what we do is we look at the shapes of the really distant blue galaxies. We look at how they've been distorted by the gravity of the foreground yellow galaxies, and that tells us how much dark matter is there. Nobody knows what dark matter is, but I have decided it's pink. So that is where the dark matter is in this particular patch of sky, and this confirms our hypothesis that the dark matter is dictating where and when the galaxies form. So where all of those big yellow galaxies were, they're all clustered together and they are housed within a giant clump of dark matter. And you can do this across the whole sky. And you can make a map of dark matter. So this is one of our most recent ones. The blobby bit in the middle is real dark matter, where you see something that's yellow, that's where there's lots of dark matter, and as it goes dark, there's less dark matter. And it's not as good as the simulation yet, which is what I set out to do too many years ago, but we're getting there, and we can make these maps now on very, very large scales. So I can tell you where the dark matter is, I can tell you how much dark matter there is, but I can't tell you what the dark matter is. But I look to my colleagues at the Lux Zeppelin project. This is a deep underground layer where they detect dark matter particles by looking at how they interact with very heavy xenon particles. So the idea is dark matter particles are flying through the Earth all the time, and the idea is they come in, they're going to collide, have a direct collision with a xenon particle. That's going to produce a little bit of energy, which is going to release an electron, and that's going to be detected. They've been running projects like this for many years and they haven't found anything yet, but the next one is going to be 10 tons of xenon, and they really, really should find something if there's something to be found. So watch this space for the dark matter detectors. It's going to be extremely exciting. The reason why it's so difficult to find them, by the way, is you can imagine the dark matter particles as just being really, really, really tiny. So, take yourself back to pre-lockdown days when you would go to the, what's the shopping street in Bristol called? I can't remember the name of it. Sauchiehall Street's Glasgow. Somebody tell me the name of the main busy shopping street in Bristol. Are you there, people? It's like on a hill going up to the university.
White Ladies Road? Is that the one you mean?
White Ladies Road. Okay, right. I want you to imagine that you're on White Ladies Road, pre-lockdown. It's really, really busy. All right. And as you're walking down it, you're crashing into people. You just want to get to FOP to buy your vinyl record or whatever you people buy. And you can't get down because it's so busy. Right. That's what normal particles experience on Earth. Right. The dark matter particle is just like a little teeny tiny ants walking down the street. They're completely oblivious to everything that's going on around them. They're just tiny ants and they just have no idea what else is going around them. The dark matter particles are minuscule compared to the other ones, and so they just fly through most of us. But in the time it takes between now and you going to bed tonight, there will be at least one direct collision between a dark matter particle and a particle in your body. And that's the technique that these guys are going to use and gals to detect dark matter. So I feel quite soon. If not, we really do have to think about things again. But let's move on now to think about dark energy. Okay, so dark energy definitely exists because a Nobel Prize was awarded for it. I love this picture. This is a picture of the Nobel Prize winners from 2011, Saul Permitter, Brian Schmidt and Adam Rees. And I want you to just take a moment now to look at the beautiful body language in this image. Now, there were two competing teams who were trying to make a measurement of how fast the universe was expanding by looking at dying stars, supernovae, which always emit at the same brightness. And so you can use them to map out how fast the universe is expanding. All right, Saul Permitter, who is on the left-hand side of our image here, was the big US project. Huge amounts of funding, massive telescope, massive team of researchers, came up with the idea, was spearheaded the whole thing. Amazing, amazing scientists, had all of the backing. Published some early results saying everything's as expected, the universe is expanding at a constant rate. Very good. Meanwhile, in Australia, Brian Schmidt and PhD student Adam Rees, so the two on your right are PhD supervisor and student. Very small telescope, tiny team, plucky Australians. We're just going to observe as much as possible. Got lucky, had slightly more supernovae than the Perlmutter team had, and found this amazing result that the universe expansion was accelerating. Now, had it just been the plucky Australian team, everyone would have gone, no, that's ridiculous. That's ridiculous. We can't simply have some energy source popping out of nowhere, causing our expansion to accelerate. But then about 2 months later, the Perlmutter team, the big team with the big telescope and all of the ideas and all of the original research, got more data and found exactly the same thing. So that is how you ended up with both of these teams getting the Nobel Prize for the discovery of the accelerated expansion of our universe. Now, I have had lots of PhD students and I get on with my PhD students a lot better than it looks like Schmidt and Rees are getting on with each other there. Look at that body language. They all hate each other. It's brilliant. Good. That's what happens if you win a Nobel Prize. Anyway, what could this mean for science? So here's a scary equation. This is Einstein's field equation. For those of you who have taken a general relativity course, you'll feel really happy at this point. For those of you who haven't, you're maybe panicking, but don't worry, you don't need to know what any of these ingredients are. On the left-hand side of the equation, you have terms that tell you about the curvature of space and time. On the right-hand side of the equation, you have terms that talk about the mass and the energy content in the universe. And what these equations say is, if you read it from left to right, it says that the curvature of space and time tells mass and light how to move. And we saw that earlier with the lensing movie I showed you, that the light was bending because of the curvature of space and time. But you can also read it in the other direction, which is that mass and energy tells space-time how to curve. So the mass was curving the gravitational field and curving space and time. Now, this little ingredient here, this lambda, is the cosmological constant. You may have read New Scientist articles that call this Einstein's biggest blunder. But I was at the Royal Astronomical Society once and I met this really nice old dude, and he said that he knew Einstein, which I'm sure can't be right, but maybe, or he knew his, anyway, but he said there was no way he would say such a thing. So was it Einstein's biggest blunder or not? Point is, this term is only there because it's mathematically possible to have it. So when you derive Einstein's field equations, which if you take a general relativity course, you guys will, if you derive it, you can include this constant as a constant of integration. So whenever you do integration, you can always put in a constant. So that's why it's there, just because mathematically you can put it in there, but there's no physical origin for this term to be there, or is there? So that's my cat wanting back in again. She'll stop trying to get in the door. Good, right. All right, so there is a theory that would predict a constant source of energy, like which would fit this term, the cosmological constant. And to explain that, I like to call this the physics of nothingness. So there are huge patches of the universe where there's absolutely nothing, there's no galaxies, there's no light. But quantum physics tells us that where there's nothing, there actually is things. If there's space and there's time, then there's the opportunity for particles to pop into existence. And they can pop back out again as well. But if your volume of nothingness is expanding, which is happening in the universe, then there's more opportunity for a particle to pop into existence than there is for it to pop out of existence, okay? And it's just to do with the growing volume of space. And in doing so, you build up energy. These virtual particles give energy to the system, which causes the universe to expand even faster, which gives more opportunity for virtual particles to pop into existence, more energy, etc., etc., etc. You can measure this effect in the laboratory. This isn't just some weird quantum story I've made up. This is a real effect. It's called the Casimir Effect. The problem is, if you calculate how fast our universe should be expanding if this cosmological constant in Einstein's field equations was sourced by vacuum energy, we wouldn't be here. The first stars and galaxies would have never formed, and we wouldn't be here to be talking about it. So that kind of rules that one out, and it leaves us with a really unclear model for what the dark energy could be. It could be a new force field. So we know that in the very, very early universe, it experienced a very rapid period of inflation that came from the unification of the four forces that we know and love now. Maybe there's a fifth force out there. Colliding brainwords or multiverses. Maybe there's another dimension out there that is interacting with our four dimensions. Maybe there are multiple universes and we just happen to be in a freaky one. Maybe our theory of gravity is wrong. So everything I've told you about so far, or the whole story I've told you so far about why we need dark matter, from looking at the rotation curves of galaxies, what this cosmological constant comes from, it all comes from Einstein's field equations and general relativity, but maybe that's not a full description of our universe. So let's just take a brief moment to go down this alley. Our first understanding of gravity came from Newton. He said gravity was stuff attracts stuff, apple falls on head, okay? And he said that gravity was a fundamental constant. It was the same everywhere in the universe. Einstein said, no, it's not stuff attracts stuff, it's that gravity bends space and time and therefore things roll together. But that happens in a constant way across all of space and time. So big G, the gravitational constant, is fundamental. So what we've been playing around with is, could gravity bend space and time differently? We know from our own experience that space and time are different. I can go any way I like in space, up, down, left or right, but no matter how much you might want the last half an hour of your life back, it's gone. You cannot go back in time. So we know space and time are different. Maybe gravity affects them differently. Is the gravitational constant really a constant everywhere? So some of the models we look at, we allow gravity to change depending on how dense the environment is. Like, we know general relativity works on Earth perfectly. If not, your GPS on your phone would not work, okay? General relativity is correct on Earth, but maybe in other parts of the universe, which are very different from Earth, maybe gravity works differently. How are we going to test all these different theories? Well, we can use exactly the same lensing that I was showing you beforehand to test out these theories. So I'm going to show you another movie. Here I've got two universes. On the left-hand side, I've got one where there's just dark matter and gravity. And on the left-hand side, I've got dark matter and some dark energy, okay, a model of dark energy. What I want you to notice is that the structures, so gravity is putting these structures together, but if you've got dark energy in there, it makes it harder for the structures to form because the volume of the universe is growing rapidly. So if we had a way that we could map dark matter at different epochs in the universe, then we could see how dark energy is changing things. And the method that we're using is testing gravity itself. So we can also test these different gravity theories as well. So that's exactly what we did. We looked at the shapes of distant galaxies, we mapped out the dark matter, and that tells us about the dark matter in about the last 6 to 7 billion light years. But if we want to look at how dark energies change things over time, we need to also compare to the universe right after the Big Bang. And luckily, we have an amazing data set to do that as well. You may have seen this image before. This is a very iconic image of the cosmic microwave background. This is what the universe looked like right after the Big Bang. And it tells us a huge amount of information about what the universe looks like. The cat has come in. And we can compare the different models. So what we did was we said, okay, let's look at the data from the cosmic microwave background right after the Big Bang. What does that tell us about dark matter today for a model where Einstein's theory of general relativity is correct and dark energy is Einstein's cosmological constant, so that number in his field equations. So we're taking another trip back down memory lane. This is one of my previous teams when I lived in Canada. We get the best dressed team award for this one, another fantastic team of people. So my only sciencey plot to show you. So there are these two numbers that I can measure when I am looking at the universe. How clumpy is the dark matter is on this axis and how much dark matter there is, right? So if I've got lots of dark energy, then I don't expect the dark matter to be that clumpy because the dark energy sort of slows down the clumpiness of the dark matter. Now, the bananas that you can see here come from a project called the Canada-France Wide Telescope Lensing Survey. Exactly the same. The grey circle here, however, is what you get from the cosmic microwave background. So that tells you about what the universe looks like right after the Big Bang. And what you can see is these two things don't agree with each other. Okay, so if in our model where Einstein's theory of general relativity is right and dark energy is this cosmological constant, data from right after the Big Bang disagrees with our measurements today using that lensing technique. Now, I find talks like this usually quite cathartic, so I want to share with you another mortifying experience, because I started off the talk by sharing a mortifying experience, so I thought I'd share another one with you. At this point in my career, I was just a postdoc, so I don't know if any of you are planning to carry on in academia, but the way it works is after you finish your degree, you do a PhD, and then you do lots of research positions in lots of different exciting places around the world, and then eventually you'll end up as a lecturer. So this was during my time when I was still doing exciting research positions around the world. And I would go and give these talks. Thankfully, my son wasn't at all of them. People would look at this plot and they would say, but Einstein's theory of general relativity is correct. Dark energy is a cosmological constant. Catherine, you are doing something wrong. And it's really embarrassing to be told you're doing something wrong in front of a big audience. And so when I moved back to Europe and I decided it was time to do another project to make these measurements again, to do bigger and better, and the cat walks back out again. It's just getting embarrassing. Cat, you are really annoying. I hope you're all amused. I hope you're all amused by the cat crisis. I'm going to go down some mad cat lady. Okay, yes. Thank you, Francis. Okay, so picture the scene. I'm just a young postdoc. I've shown these results. I've been working on them for years and years, and the establishment disagree. The establishment think that this is wrong, and therefore I must have done something wrong. And every single talk I would give, the establishment, the typically old white male professors would stand and go, Catherine, can you tell us what you've done wrong? So I really wanted my next project to be right, i.e. I wanted to agree with what the establishment said was right. And that's a really bad way of doing science, people, okay? So we don't understand dark matter, we don't understand dark energy. We need lots of different experiments to try and test it out. And if you have this like strong opinion of the result that you want to get, then you're not doing good science. The result is what it is. It shouldn't be what you want. So I want you to think about that actually for your own projects, and like, when do you decide to stop? When do you decide you've got the answer right? And it's really hard to do. So what we did was we created 3 different versions of our data set. All right, so here are 3 different pictures from my survey. One of them's the truth, and the other 2 have been morphed just slightly. And what we did was we analysed all 3 of them, and we wrote 3 different versions of the papers that gave us 3 different answers that we could test our different models of gravity and dark energy and dark matter. And only when we were absolutely happy did we unblind and find out which one was the truth. And here's that same plot I was showing you before. So this is how clumpy is the dark matter on this axis, and how much dark matter there is. And this just came out just a couple of months ago now. So if I compared it to the previous plot that I saw you, the bananas are much shorter now, but still they'd hardly agree. So something is up, something is strange. What these results mean is, if you look at the universe right after the Big Bang and you ask what it should look like today, what we're finding is that it's too smooth. Okay, the dark matter distribution that we find is much smoother than we'd expect from our model that of Einstein's theory of general relativity, cold dark matter, and a dark energy that looks like Einstein's cosmological constant. If it was just us finding this, I think I'd still be meeting that Catherine, what have you done wrong? But luckily, that wonderful Nobel Prize winner, Adam Rees, that we saw at the start, let's just remind ourselves what he looks like. Where is Adam gone? Yeah, there he is. So this guy on the left here, Adam Rees, after he found out the acceleration expansion, he's gone on to carry on measuring the expansion today. And he finds something different as well. So he's finding that the universe, sorry, just going back to the right slide, he's finding that the universe is also not expanding as fast as you would expect from our understanding of the universe given by what's happening after the Big Bang. So really exciting times in cosmology at the moment, because if our results are right and Adam Rees's results are right, what it means is that our model of the universe is even more complex than we thought. We don't know what the dark matter particle is, and the dark energy that we seem to be measuring is not behaving like Einstein's cosmological constant. So we're testing lots of different theories, we're having lots of fun, but we need more data and we need more scientists like you to come and work with us. So exciting times ahead. This is, it's no longer, I need to update my slides. This is the Vera Rubin Observatory. It is currently being built in Chile. This is going to survey the entire night sky on repeat. Every 3 nights. This is the way it works in the US, people. If you want money, you have to like have a really big, exciting story. So the clever scientists in the US went to Congress and they said, killer asteroids are going to obliterate us. We need a really big telescope to map them all out, and then we can mobilize Bruce Willis to save us. Yes, Congress shed loads of money. Brilliant. Actually, what we're going to do with it is understand dark matter and dark energy, but we'll also find the killer asteroids as well. Very exciting new project. What the galaxies look like though from the ground, okay? The atmosphere really kind of messes everything up, and if you're looking for those tiny distortions that dark matter introduces, you need to go into space. And that is exactly what we're going to be doing. And we are launching the Euclid Space Telescope in a couple of years. And it's going to be the combination of both the Vera Rubin and the Euclid Telescope from ground and space that is going to give us the dark matter maps that I've shown you across the entire sky, and looking at how that's changing with time to compare, to confront all of these different theories about what dark energy is, what dark matter is, and how that's evolving in the universe. People often ask me, well, what do I think they're going to find? I hope we find something that really makes us think, because at the moment I feel really embarrassed telling people that there's this dark matter and dark energy out there that we don't really know what it is. So I'm hoping we find something that allows us to really dig down and explain these dark entities in our universe. That's what I hope. What I fear though is that we're just going to end up with a result that we don't really understand, and we're going to have to resort to the multiverse description of our universe, that we just happen to live in a weird one and we don't really understand why. So fun. That's a whole other talk that if you want to invite me back another time, I can talk about the multiverse and everything we know about it. But here we go, my final 3 slides. Dark matter has to be there. If it's not, our Milky Way galaxy would fly apart. Dark energy appears to be there. It's speeding up the expansion of the universe. And the reason why you should be excited about these 2 things is we don't understand them. Our current understanding of physics cannot explain these 2 entities. They do not fit in with our current fundamental knowledge of physics. So there's something missing there. And that's why we're really excited about you guys coming and learning physics and teaching us all that we need to know about the dark universe. I will wrap up with 2 plugs. This is a book I wrote. It is free to read, and it's really short because I like short books. This is sort of brings you up to date on all of the different ways you can explore the universe using telescopes. Oh, but something just, oh, my sorry, my slides just decided to stop working. Let's see if that's working. Okay, there we go. And you can also take a course, or if your parents are like, oh, we don't understand what you do, this is a course maybe for them. Again, free online, and I will leave it there. Thank you so much for inviting me to come and talk to you this evening, and apologies for mad cats.
Oh, thank you so much. And I think the mad cat made it, I'd say. Someone has written in the chat, loving the cat updates. You've obviously got a very scientific cat wanting to get. But no, thank you so, so much. And I would like to open up to questions now. I know usually what we do, we just make you write in the chat. But if someone wanted to be brave and turn their mic on, or just turn their audio on and have a bit more of a chat, then that would be really welcome. But yeah, if not, do leave your questions in the chat for us. Oh.
The cat's called Tiki. But I didn't name the cat. What happened was, Edinburgh is like this really old town, and we live in this like super duper old tenement block that's got huge loads of flats left, right and centre. And there was one night in the kitchen where a mouse ran across the kitchen. I was like, ah, it's a mouse. And literally at the same time, a thing flashed up on Facebook from one of our friends saying, oh, we can't keep our cat anymore, we've got allergies, can someone take our cat? And I was like, take the cat. And now we have a mad cat, but no mice, so that's good.
Yeah,
we can talk physics as well as my cat though.
cool. Ailish has written, if the dark matter detectors haven't found anything, what is the day-to-day of the research like?
So I'm not a dark matter detector person, but I work with a lot of them. So most of their time they're spending designing the next experiment. So these big vats of xenon, they just get bigger and bigger each time, but they have to sit in these deep underground, like the bottom of salt mines, where they're kind of shielded from a lot of the other particles that could be detected. So they spend most of they build a new experiment, and then they bury it in the ground. Well, they don't bury it, but they take it deep underground, and then they leave it for like 2 years whilst they're designing the next experiment, and then they open it up to see what they find. So it's a waiting game. But there's new technology there as well, where they're looking at using argon to detect things, which is a lot cheaper, but then you need much more of it. And the last thing I saw, they built this massive tower that's like almost the size of the Eiffel Tower underground. It's insane what these guys are doing, and girls. It's a really amazing project, and I just really hope they find something, because if it would be, if the dark matter particle isn't weakly interacting, you won't detect it using these methods. So there are lots of other dark matter particles out there, and there's something called axions, which are hard to detect with this method. And now people are starting to design detectors for them, just because they keep building bigger and bigger detectors for the weakly interacting particles, and they're just not finding them. And on top of that, CERN should have created one of these particles by now. CERN is working at a high enough energy range to create these particles if they exist, and they haven't seen it. So yeah, let's see.
Is there any pattern or consistency on the distribution of dark matter that we know of?
Yes, so the pattern, the cosmic web that you see, that has a very characteristic pattern that you can predict from how much dark matter there is in the universe and how old the universe is. So the idea is that basically there's a Big Bang. I don't know what caused the Big Bang. That's prehistory, but anyway, there's a Big Bang. But the Big Bang only creates a universe about the size of a pea. It's really very small. And there are very tiny quantum fluctuations in that P. Then you have this period of very rapid inflation that's essentially instantaneous. So you go from P size up to sort of the large cosmological scales that we see today. That period of inflation is a sort of a transition between all of our best guess is that the four forces that we know are transitioning at that period of inflation. And that blows up these quantum fluctuations onto large scales. And it's that gives you this characteristic pattern of the dark matter. So it comes from if you just look at just random quantum fluctuations on a small scale, suddenly blown up onto large scales, and then say, how would those fluctuations now evolve over 13.8 billion years, which is the time from inflation to the present day. And then you look at that web of dark matter, it's exactly what we'd expect. So before we've made our maps of dark matter, you could just look at that in the galaxies. But now we have these large scale maps of dark matter. It's exactly the right pattern. So the number of clumps and the separation between them is exactly what we'd expect from this model of inflation in the very early universe.
So is the dark matter moving then? And what's causing it to move?
Yeah. So, I mean, everything in the universe is moving away from everything else. The main dominant force is just gravity. So where there's lots of dark matter, there's lots of gravity, and more dark matter will move towards it. But as the distances between points is expanding, because the whole universe is expanding, it becomes harder to fall into those gravitational wells. So in our current model of the universe, you have quite a sad sort of end point where the universe is expanded to such a large scale that you'll have sort of islands. Basically, you'll have clumps of dark matter where there's lots of galaxies, but then nothing else out there to see. And if you are a lone galaxy with no other galaxies around you, you won't see anything. You'll look out, you'll just see the stars in your own galaxy and nothing else, and you'll think that you're in a universe just with a single galaxy. So that's why are we, if that's going to happen in the future, how are we in this nice period of time now where we know that there's stuff out there? It's an interesting question.
Anyone else? Any questions at all? And you are welcome to speak out. No, you've obviously explained everything so well.
Excellent. Well, it's been a real pleasure to be able to come and talk to you this evening. Thank you so much. Guys, it's a really challenging time right now in lockdown, and all of us are really feeling for you, undergraduates. This is not how we want your university degree to be. We really just our hearts are broken that you are having to study and learn this way, and I'm wishing you the absolute very best with it. You're all going to be fantastic physicists, and we just all have to make the best of hybrid learning over the next year, and hopefully we'll all have you back in the labs as soon as possible, and back in proper meetings where we can actually sit and talk to each other and draw things on blackboards and get excited about physics together. But just let's get through this next wee while, and then hopefully we can all return to normal.
Oh gosh, thank you so much for coming. Thank you. Like, it's been amazing talking. You've been so lovely, and your cat has been so wonderful.
It's insane. All right, guys, very welcome. If anyone's looking for PhD places, Edinburgh's advertising some at the moment, so check out our web pages.